Hello friends, welcome back to our channel. So in today's session we'll see one more concept in compiler design, that is a code optimization or a block code optimization. So in our previous session we have discussed about the basic blocks, so how to divide the program into basic blocks and how can we connect those basic blocks by using this flow graph. So the basic block gives the structure of a program and the flow graph specifies the control flow between those blocks. And now the very important topic is code optimization. So code optimization means how the code is efficiently developed. So in terms of both the memory and also time complexity. So the main reason is fast execution. The execution will be very fast and it will reduce the memory usage. Okay, reduce the memory. So this is a time complexity and a space complexity. You might be learning about these two things, time complexity and space complexity. Time means fast execution, within a very less time we need to get the result, and the space complexity we need to use the variables or memory very efficiently. That means we can reduce the memory usage, and also if these two things happens, automatically the efficiency will be improved. So it improves the efficiency. So in order to achieve all these things, the target code should be optimized. Okay, so we'll see what are the optimization techniques. Okay, so when the code will be optimized and how the execution becomes fast and how the memory will be reduced. Okay, so we'll see the optimization techniques, so which we need to take care to generate the optimized code. So optimization techniques, the most important thing. The first technique is algebraic expression. So we need to take care about all these expressions, algebraic expressions. So we need to simplify this one. We need to simplify the algebraic expressions. So example, we know a simple algebraic thing, anything multiplied with 0 will be getting 0 as a result, and anything addition with a 0 will give the same content. So we can replace these things by eliminate these terms. So we can avoid the multiplication, we can avoid the addition. Instead of that, we can directly take the result as 0 and a in this case. So we can simplify the algebraic expressions. Okay, next, common subexpression elimination. So we need to eliminate the common subexpressions. So the reusability we need to add. Okay, so we need not compute the same thing multiple times. Okay, so we can remove such type of subexpressions. So the same thing we have learned in directed acyclic graph, DAG. Okay, so let us take some a is equal to b plus c, and there is a one more expression called d is equal to b plus c. Okay, so here you can observe b and c has been added here to get a result of a, and once again we are adding the same variables and we are storing the result into d. That means the addition operation between b and c has been duplicated multiple times. We are computing the same thing. So instead of this, what we can write, we can compute only once b plus c and store the result in a, and then same store the a value in d. So instead of recomputing this b plus c, we can use the variable where stores the result of b plus c here. So these kind of things we can eliminate. So common sub-expressions can be eliminated. Next, constant folding. Constant folding. So here we can evaluate some computations in compile time. Evaluate expressions in compile time itself. So we know the compile time and runtime. Okay, for example, you can see some a is equal to b plus c. If the same expression we need to compute, then the result will be depending upon b value and c value. So usually we are writing the program where we are reading the values of b and c during runtime. We are using some scanf in C language, right? So unless you use a scanf, we can't know the values of b and c. Okay, that is called a runtime. Runtime we are taking the inputs. So this we can't do anything. So we need to take the inputs and we need to compute the addition. But if the same thing happens in this manner, 5 plus 6. So here what happens? Here we are not taking any variables. We are taking directly a values 5 and 6. So in order to perform the addition between 5 and 6, we need not wait till the runtime. So during the compile time itself, we can compute and we can store the result. So this can be done at a compile time. So during the compile time, some sort of expressions. So these kind of expressions can be evaluated and we can replace this as a is equal to 11. So this is called as a constant folding. Constant folding. Next, similar constant propagation. Constant propagation. So here substitute the values. Substitute the values. Already whatever the values we know that those values can be substituted here. Okay. So for example, take a is equal to 5 and b is equal to some a plus 6. So what we can do, so these type of expressions can also be calculated at compile time. Okay, so because here you can observe this expression. So the addition is dependent on variable a, where the variable a is having the value 5. Already here 5 is there. So automatically the result can be stored as a is equal to 11. So this can also be computed at a compile time. So this is also one form of constant folding itself. Okay, we are supposed to substitute the values in the variables. And next, copy propagation. Copy propagation. So here the copy propagation means, and you can see some a is equal to, this is also similar to our constant propagation, but here what we have to do is, if it is a is equal to some 5 and b is equal to some a plus c. Okay, so in this case what we are doing, so we are just copying. So here you can replace this with b is equal to 5 plus c. We can simply copy this constant to this particular variable and we can replace the statement in this way. So these kind of things we call it as a peephole optimization. Peephole optimization. So whatever the things we have seen, constant propagation, copy propagation or constant folding, all these three can be considered as a peephole optimization. So reducing the instructions to make the computation in a faster manner. So in here also, instead of writing this one directly, we are replacing with this one, and here we are just replacing the variables, and here we are copying the constant to the variable. So all these three comes under the peephole optimization. So reducing the number of instructions by making with the instruction which executes faster. Okay, so that is a peephole optimization. So I'll write here reducing multiple instructions with one instruction which executes faster. So multiple instructions can be reduced with only one instruction. Okay, one or very two instructions. So reduction of instructions, that's the peephole optimization. And the next one is a dead code elimination. So this is also most important. Dead code elimination. Dead code means if we are having a multiple instructions and if one instruction is not being used so far, or then in the further instructions, so simply we can eliminate that particular instruction. So for example, let us take some a is equal to 5 and we are calculating c is equal to some 10 plus 4, and we are simply writing printf percentage d c. So what happens here in this code? So C is already computed and we are just printing the value of C. So where we are using this A value? So A value is not used in the program, but we are using the variable. We have declared some variables and we are initializing that variable with some value which is not used in the program. So this is called as a dead code. So these kind of instructions should be eliminated. So if you use all these techniques, automatically the code will be optimized. Okay, so first one, algebraic expressions. So simplifying the algebraic expressions, and then common sub expressions should be eliminated, and constant foldings, constant propagation, copy propagation, which we call them as a peephole optimization, as well as the dead code elimination. So we need to follow all these things to make the code optimized. Okay, so let us see a small example so that you can understand all these techniques. So let us take this example. So if our code is having these many instructions, we can reduce these instructions by using the techniques so far we have discussed. So these instructions can be written in the same way, a is equal to b plus c. And coming to the second one, already b plus c is evaluated and it was stored in a, so we can reuse that one. So this can be written as d is equal to a. And see here, this is simplifying the algebraic expressions. So anything plus 0 will be the same variable. So it can be written as e is equal to d. And here anything is multiplied with 1, that will become the same number. So f is equal to e into 1. So whatever the number it may be, the value will be 1 itself. So f is equal to e. And here, so this is a constant folding. So this can be evaluated during the compile time itself. So g is equal to, it can be written as 8. And here we are having, we can copy the variables. So h is equal to 8 plus f. So this is optimized by using all the techniques which we have seen, right? And next, it can also be simplified, right? More optimized. We can also make this more optimized. You can observe here, more optimized. So which is the first statement, a is equal to b plus c, and what we are doing, a is stored in d and d is stored in e and e is stored in f. Okay, e is stored in f. So obviously what happens, so f consists of e only, f consists of a value only. Okay, f consists of a value. So if a is 4, you can see d is equal to 4. So e is equal to d means e is equal to 4. Yeah, e is equal to 4 means f is equal to 4. So that means a is equal to 4 means here f is equal to a. So that can be replaced in this one, right? So second one, h is equal to 8 plus, what we can write, instead of f we can write it as a. So the entire instructions can be written in only 2 instructions. Okay, which makes it faster. So this is also called as a peephole optimization. So we are reducing the multiple instructions and making only a few instructions which will execute faster. So this is called as a peephole optimization, and here you can see whatever the techniques we have so far learned. So we have used everything to reduce the code. Okay, so these many instructions can be written in a simple 2 instructions. So this is an optimized code. So hope you understood what is a code optimization and why we are using this code optimization. So in order to make the execution fast and reduce the memory, and which improves the efficiency. The 3 points are most important. Okay, so I'll stop here, and if you are having any queries regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.